In the last video, I ended it not so well. I just want to make sure that everything's quite clear. All right. So the type 1 supernova, right, that's what they call the carbon detonation. This is a white dwarf with a companion star, right, in a binary system. Now, if we go back to when we talked about nova, right, just not a supernova, a nova, what happens? It's the same thing that happens with a nova. But see, you have hydrogen fusing at the surface, because matter from the companion star is falling onto the white dwarf. The difference, okay, so this is important. This is what I was trying to get at last time in the last video. The difference is a type 1 supernova. You still have a white dwarf. There's still material piling up on the white dwarf, but then you reach a point where the mass is greater than 1.4 times the mass of the sun, right? So recall. Let's see. Did we have that? Let's see. Where did we first talk about that? I know I'm going back several slides. It might have been in the last. Yeah. So this is the white dwarf. Anyhow, 1.4 times the mass of the sun is called the Chandrasekhar mass, and what that does. Let's see. Is this where it talks about it? No. What that does is when you reach, so if a white dwarf reaches that amount, right? So 1.4 times the mass of the sun, which if you think about it, a white dwarf is pretty close to would be around the mass of the sun, probably less, up to about half the mass of the sun, or down to about half the mass of the sun. And so if it's accumulating matter, and that reaches that critical point where it's 1.4 times the mass of the sun, then what happens is you have this incredible implosion, and that's the type 1 supernova. Okay, so that's what this is. Right? So that's the green line right here. All right. So we often will call that a carbon detonation because you're talking about a white dwarf exploding. Right. So the type 1, we suspect all theoretical calculations show that there's very unlikely, I should say, that there's any material left. There's no no stellar remnant at all left. Just an explosion that is spreading heavy material out into space. All right, and we're going to find it's not just carbon that's being spread out into space. There are other things as well. All right, now the type 2 supernova. Okay, so that's the one with the plateau here. Now that is a truly massive star, not a white dwarf that is accumulating mass. I mean, this could be a single star that is like more than 8 times the mass of the sun, and maybe even like 20 times the mass of the sun, and that will reach the moment it reaches iron, then that particular star explodes. All right, so let's go. Oh, here's the 1.4 times the mass. there it is. All right, so carbon detonation. That's what I was just mentioning. Remember, we're talking about a white dwarf in a binary system. So the white dwarf, right, that's a star that's already died, and is accumulating mass from its binary companion, as it says. So so only if it reaches this 1.4. I know I already said this, but once it reaches this amount, and if it does, it doesn't always, then what happens is this is actually what Chandrasekhar, the person, the astrophysicist, won a Nobel Prize for, is he calculated that it would take this amount, 1.4 times the mass of our sun, for electron degeneracy to not be able to hold back the star from gravitational collapse. And so that leads to our type 1 supernova, right? And so it explodes, you get incredible amounts of carbon, nitrogen, oxygen, and other heavier elements, as we're going to see, to a much lesser extent. There's some of these heavier elements that these type 1 supernova expand out into the universe. All right. So and the other thing about this, these type 1 supernova, they also call them carbon detonation or carbon explosion supernova, is we don't think that there's going to be very much stellar matter left over. Okay, so that they explode and just about everything goes out into the universe. Now, it expands and reseeds the interstellar medium. All right, so let's get on. So this is just showing the two different types. Okay, so you have this white dwarf. It has a companion, and if let's say the companion is far enough away that matter's not being exchanged, but then the companion dies at some point in the future, and then you have this white dwarf that's been orbiting it for maybe many millions, even billions of years, and as the companion star expands, material will actually fall onto the white dwarf, and if that amount of material reaches more than 1.4 times the mass of the sun, then the white dwarf can't support itself. Remember, the inward force of gravity has to be matched by an outward pressure, and the problem is the outward pressure would have to be electron degeneracy pressure, but that it won't be able to support that, and so it explodes, and then there's pretty much nothing left afterwards. All right, for a type 2 supernova, this is starting out as a very massive star. Remember, these things can start off. The type 1 can start off as something usually more massive than the sun, up to about roughly 8 times the mass of the sun. But these are starting off more than 8 times the mass of the sun. Okay, so these are dying stars, and you have an incredible amount of material mass that is crushing this star down, and so it fuses heavier and heavier elements. Remember, you basically have these shells of heavier and heavier elements, and we're going to see the statistically what elements the star will create in greater abundance than in others. Right? It's not all exactly equal, and that has to do with the alpha process, the helium mixing with the next heaviest element. Anyhow, as this stuff develops eventually an iron core, then that iron core cannot support itself and collapses onto itself, and then a whole bunch of neutrons and neutrinos are created, and the neutrinos escape out into the universe, and they were actually carrying most of the energy of this type 2 supernova, but there's an incredible amount of energy that is seen in the electromagnetic spectrum, in the visible, in the X-ray region, and so forth. Even some in the gamma region. All right, so here's an example of a type 2. Remember, the type 2 supernova leave a star behind, or, some remnant behind. Um, not okay. A remnant in the sense that there's in the middle of that remnant there's still some stellar material, right? A very, very dense stellar material, which ultimately is going to be what we're going to call a neutron star, right? That's really the subject of the next chapter, but we're encountering it here. So back in the year 1054. In the Common Era, or what used to be known as 1054 AD, more than 1,000 years ago, there were Chinese astronomers that noted a star in the constellation Taurus, and that star, it was so bright that they said that it was actually brighter than the full moon, and in fact, you could, according to some reports, you could see the star during the day. It was that bright. And also, there's even other reports that said it was bright enough at nighttime that you could even read by the light of this star. And that it lasted for, the light that they're talking about lasted for about 150 to 200 days. All right. And so what we can do now, of course, is we look at the stellar remnant, and this is material that's flying out from some central region, and of course there's where the central region is, and we can you measure the velocity of this stuff, and then you figure out how much time did it take this material to get to where it is, and you can measure how fast it's going by using the Doppler shift, and the Doppler shift tells you exactly how. Usually we measure that in kilometers per second, and so you can extrapolate back and figure out when the explosion took place. And of course, the explosion took place in the year 1054 AD, or BC, BCE. CE, the common, in 1054 in the Common Era, also known as AD. All right. So anyhow. That is that's a very well studied supernova remnant. Here's another one called the Veil Nebula. I forget what constellation this is in. Let me think. It doesn't really matter. All right. Anyhow, this is a very wonderful looking nebula. It doesn't look like this in a telescope, mind you. This is in what they call false color to emphasize the different parts of this nebula. We think that this one, according to the speed and working backwards, we figure that this happened in the year roughly about the year 7000 BCE, before the Common Era, or also known as BC. This is really when civilizations were just starting. Well, agriculture probably had been around since about 10,000 BC. I don't know that we have any actual records, any written records of this. Anyhow, here is a much more recent supernova. There's actually supernova in our galaxy, right, in the Milky Way galaxy, which is, again, this collection of stars that are gravitationally linked, that there's about 200 billion stars, roughly, in the Milky Way galaxy. And we haven't seen a supernova occurring in the last 400 years. And it turns out that about 400 years ago, that was the time of Kepler, and there was another guy that Kepler studied or worked with named Tycho Brahe, and Tycho Brahe actually saw a supernova, and just a few years later, Kepler actually saw a supernova. And but the most recent one that has been closest to us was not in our galaxy. It was in a neighboring galaxy called the Large Cloud of Magellan. This is a satellite galaxy that you can only see in the southern hemisphere, there's actually two of them. One's the large cloud of Magellan, the other's the small cloud. These are